So VBT, Valence Bond theory. You see, it is one of the approach to explain the nature of the coordination covalent compounds and its bond. So what are the other approaches we have to explain the nature of the bond present in the coordination compounds is here it follows crystal field theory, ligand field theory, LFT will say, and MOT, molecular orbital theory. What exactly these theories are going to describe about the nature of the coordination compounds means they are going to see the geometry, how the geometry of the coordination compound is there, and what type of magnetic property it is exhibiting, and what type of hybridization is responsible for these two properties. I can say geometry and the magnetic property. They are based on the hybridization, right? According to this theory, the central metal atom or ion under the influence of ligand, it may use its n-1d inner orbital or ns, np and nd valence shell orbitals, or it can use its valence shell electrons from respective orbitals like ns, np and nd orbitals for hybridization to yield equal energy containing same number of hybrid orbitals that can overlap with electron pair donating ligand orbitals. Based on the spectrochemical nature of the ligands, ligands are divided into strong field ligands that promote inner orbital electron pairing in inner orbitals, that is n-1 d orbitals. So second group is weak field ligands that will not influence the electron pairing in the inner orbitals, that will utilize outer shell orbitals for linking, not the inner orbitals. Inner orbitals means n-1d orbitals. So here we will take a couple of examples of coordination compounds with strong field ligands and weak field ligands. So first we will see examples for strong field ligands and weak field ligands. Under strong field ligands, I have took cyanide ion and neutral molecule ammonia. Under weak field ligands, halides, I have took fluoride ion and chloride ion. So if you try to describe the coordination compounds with these ligands, strong field ligands, cocamps, and weak field ligand cocamps, if you take. So if you write the IUPAC names of these particular compounds, hexaamine cobalt 3. Why we have written like this? Cobalt is the central metal atom here. 6 amine groups are there. 6 ammonia groups are there. But you have to write like it is amine, double M you should write for this ligand. And 6 are there. That's why we have written like that. Cobalt is present in complex cation. That's why its name will become normal. English name only, cobalt parenthesis 3, Roman letter 3. That is the reason why we have written cobalt 3 in parenthesis, small bracket, right? So if you take the next compound, tetracyanido, Cn minus is cyanide ion. We will remove E and we will keep O. That's why tetracyanido. Cyanide will become cyanido here, right? Tetracyanido. Nickelate 2. Nickel is a central metal atom whose oxidation state is +2 here. And moreover, central metal atom, nickel is present in the complex anion. 2-, right? Entire coordination sphere charge is 2-. So it is central metal atom, if it is present in complex anion, its name will be written as 8, nickelate. That's why we have written nickelate. So the compound name will become tetracyanido nickelate 2. So like that, weak field ligand names also will go through once. So here it is a complex anion in both the cases. Nickel as well as cobalt are present in the complex anions. So nickel is present in 2 minus charge in this anion, the entire complex. The what do you say, oxidation state of nickel is +2 here, and it is present in complex anion, right? So then the name will become tetrachlorido nickelate 2, parenthesis 2. So like that, hexafluorido cobaltate 3. Central metal atom cobalt is present in the complex anion, that's why cobaltate 8 we have to add, right? And in the parenthesis the respective oxidation state will be mentioned in Roman letters. So these examples, these 4 examples, we are going to describe the nature of coordination bond present in the compounds. So which will give the hybridization of the coordination compound, which will also describe the magnetic nature and the geometry of the compounds. So now we'll take coordination compound with linked with strong field ligand. So that is hexaamine cobalt 3 coordination compound. So basically here the central metal atom is cobalt, whose atomic number indicated by Z is equal to 27. What is the oxidation state of central metal atom? These are the tips what we have to follow while describing the nature of the coordination compounds with the approach of valence bond theory. So first thing you have to see the atomic number of the central metal atom. First means you have to identify the central metal atom. So central metal atom is cobalt here, whose atomic number is 27. We have identified central metal atom, and we have to find out the next step is oxidation. So oxidation state, here we can see cobalt linked with a neutral strong field ligand ammonia, whose charge is 0. So 6 molecules are there, but for a molecule charge is 0, that's why cobalt plus 0 is equal to the whole complex is a cationic complex, so is equal to +3. That's why cobalt, the central metal atom, is having an oxidation state of +3, means cobalt is releasing 3 electrons from its original atomic configuration. What is the original atomic configuration? Here we are seeing CO is equal to 22, right? CO is equal to 27, sorry. Here we are seeing CO is equal to 27. So you can see here, right? 27, right? 27. So we will write, simplify by taking the nearest noble gas configuration. We can write the configuration by taking argon 4s2, 3d7, 4p0, 4d0. So this is a general way of writing the electronic configuration according to Hund's rule. By filling, Aufbau's rule, Hund's rule, all these things. So, but for our convenience here, to describe the nature of the coordination compound, we are just simply rearranging the configuration according to our convenience. So argon 3d7, 4s2, 4p0, 4d0. This is the original atomic configuration. But cobalt is existing in the form of CO3 plus. CO3 plus. Cobalt is existing as 3 plus ion. So it has to lose 3 electrons. If you write the configuration according to this one, what will happen now? It will be like this. So from where the electrons will be removed during ionization? From CO2, CO is converted to CO3 plus. So by releasing 3 electrons, right? 3 electrons. How they are released? It is from 4s. 4s 2 electrons are released, and from from the second orbital. Suppose if you take this as dxy, this is dxy, zx or this is zy. You can, this is dx square y square and this is dz square. So from dxz, one electron is removed. So total how many electrons are removed? This is crucial step from where it is losing the electrons. So 2 electrons, total 3 electrons cobalt has released to convert into CO3 plus. This is the original oxidation state in the coordination sphere of the central metal atom. Now it is linked to 6 molecules of strong field ligand. So each strong field ligand will contribute a pair of electrons in the form of a D2 bond to form a D2 bond or to link up with the central atom whose is 3 plus. Then it means that cobalt 3 plus has to provide 6 empty orbitals like this 6 empty orbitals for the accommodation of 6 pairs of electrons from 6 ammonia molecules. Means total 12 electrons will be contributed by 6 ammonia molecules, which is a strong field ligand, to link up with the cobalt to form 6 coordinate bonds. For this, because of the nature of the ligand, strong field ligand, it always promotes inner orbital pairing, right? Inner orbital pairing. How it will pair? So same after losing electrons, this is the configuration. So this last electron present in the dz square will pair up with the electron present, half electron present in the half orbital. One electron present in the dzx. dx square minus y square. This is x square minus y square orbital. So this electron will pair up with the next orbital electron yz, dyz. You can write dyz here. This is dx z or zx, you can say. So what will happen after pairing? Inner orbital pairing. It is called low spin complex, we will say usually. So inner orbital pairing has happened due to influence of the strong field ligand. So after that, what will happen? The inner orbital is n minus 1d, right here. So it will have 3d6 electrons after pairing, and 2d orbitals are empty. X square minus y square and dz square. So these two are empty. Dz square are available for the receiving of pair of electrons from two ammonia ligands or two ammonia molecules. Here one is available. So total 3. 2d are available from inner orbital, that is n minus 1d, that is 3d orbital. 1 from the valence shell s orbital, 4s, and 3 orbitals from completely, they are also already empty. So that's why 3 empty orbitals will be procured from the 4th shell p orbital. So total 2d plus 1s plus 3s plus 3p. Total you will have 6 orbitals. After hybridization, it will produce 6 equal energy containing D2sp3 hybrid orbitals. All will contain equal energy. That is what all this one is D2 sp3 orbitals. All these 6 are D2sp3 orbitals. So this is the remaining inner orbital 3d. This is 4d. Total you will have 6 orbitals which can accommodate, here you can see, which can accommodate all 12 electrons donated by the 6 ligands which are strong in nature and form 6 links with the cobalt present in the coordination sphere, central metal atom. So what will happen like this? Like this you can show day2 bonds, right? All are day2 bonds. You can show like this, arrow mark like this. So if you see the structure, you will have a geometry of octahedral geometry. So easily understand that geometry will be octahedral geometry if you connect all the atoms which are linking up with the central metal atom. So if you observe the configuration, there is no half-filled orbitals. Means no electron is freely available. No half-filled orbitals, completely filled orbitals, which indicates that no free electron means no unpaired electron. So which indicates the magnetic nature of this coordination is diamagnetic. So how we have described the parameters of the coordination compound having strong field ligand? So here three parameters we have described. One is its, I mean, this coordination covalent compounds hybridization is D2sp3 that we have found out here. Then we have seen the geometry after hybridization. The geometry we came to understand it will form octahedral complex. After that, if by observing the electronic configuration, we came to know that there is no unpaired, which indicates the diamagnetic nature of the coordination compound hexamine cobalt 3.